Let us open Ansys workbench and load the input BladeGen file. Let us open pump_input. Click OK for this warning. We can check the blade design in BladeGen. Click here. We can see the pump flow path here. We can see the 3D model here. Click OK. We can see multiple sectors or single sector here. Now we shall not modify any geometry. We shall directly transfer this data to TurboGrid, create the mesh, and then if required we can modify the BladeGen based on the performance output. Now we shall close BladeGen, right click blade design and then transfer to new TurboGrid. You can right click edit. TurboGrid sector model is automatically created. We can extend the domain at the inlet and outlet completely. We can uncheck this suspend object updates. The mesh has been generated. It is showing some warning, we can ignore. This is about inlet and outlet domain, not created. As of now we don't need this, so we can click OK. I will quickly change the settings to get desirable mesh. Now mesh has been generated with no errors. We can close it. Now right click turbo mesh and then transfer data to new CFX. Right click setup and then click edit. Now preprocessor is open. We can directly specify the boundary conditions in turbo mode. Go to tools, turbo mode. Here we can see the arrow pointing in the wrong direction, so we have to change the RPM sign. The axis is Z axis and the machine type is pump. The analysis is steady state. Click next. In the components we have to specify the RPM 5000 in negative direction. Click next. We shall specify total pressure inlet and mass flow outlet. Inlet is 101.325 kilopascal. Flow direction is normal to inlet, and mass flow outlet is per machine. It means it is the overall mass flow rate. You can choose per machine and specify 6 kg per second. Here you have to change the fluid data to water and then change the reference pressure to 0 atmosphere. And let us not choose any heat transfer option for this, since it is a pump model. However, users can try total energy and then compare the results with no heat transfer option. Now click next. This is the R1 to R1 periodic interface. It is chosen by default. Click next. These are the boundaries: R1 blade, hub, inlet, outlet and shroud. Click next and click finish. We can create expressions for monitoring mass flow inlet, mass flow outlet, pressure rise and other parameters whatever required. I am skipping that part as of now and then going to CFX solver. Close preprocessor, double click solution. Now we can specify the run mode and start the analysis. Now the solver has started. I am skipping the iterations. I will directly go to the result and show the calculations. Now the solver is complete. We can post process the results. Go back to workbench and edit CFD post. In the post processor we shall go to turbo mode and initialize all the components. Calculate velocity components and come back to outline. Now we can choose the regions and then duplicate the number of blades. We can hide the wireframe go to turbo surface, click turbo surface. We shall plot total pressure and then check the total pressure distribution. This is in relative frame. Let us choose stationary frame. Now we shall see the total pressure rise in the pump. Next we shall check the torque and power values. Go to table, click table 1, OK. Torque. Here the axis is Z axis. So choose torque at Z axis. This is for one blade. We shall find out the torque for all 6 blades. Next we shall find out the flow rate as well as pressure at the outlet. For volume flow rate, we have to divide by density. We have to specify the units also while dividing. Now it is in meter cube per second. Next we shall find out the total pressure at the outlet. Mass flow average of total pressure in stationary frame at physical locators R1 outlet. Click OK. Let us remove the units and keep only the absolute values. Now we shall post process the results and then find out the power required and efficiency. We shall specify the units. We shall calculate the volume flow rate again. Now let us find the outlet pressure in gauge terms. So this is the rise in pressure, that is rho GH, and when we multiply this by the volume flow rate, we will get the flow power. This is in watt. Now let us find out the power required for driving the pump. This is given by torque into omega, so we shall multiply the torque for all blades into omega. Omega is 2 pi n by 60, where n is the RPM. So this is the power required or supplied, and this is the net flow power gained. So the efficiency is given by flow power by required power. This is for compressors or pumps. For turbines, it will be the reverse of that. The efficiency is close to 77.3%. Final results are tabulated here. You can have a look. Okay, thanks for watching this video. I will see you in the next lecture.